Hello YouTube, I'm back. Today we'll be covering complex analysis. More specifically, we'll be proving that the integral from 0 to 2 pi of Poisson's integral with respect to d theta is equal to 2 pi. And what is Poisson's kernel? Well, Poisson's kernel is this funny looking expression here. 1 minus a squared over 1 minus 2a cosine theta plus a squared. And Poisson's kernel has many applications in various fields of math, but one notable one is in partial differential equations, where you'll use it in this thing called a Dirichlet boundary or Laplace's equation, which is this differential equation right here. And I probably butchered this name here, but I don't care. Okay, so now we have the integral of the Poisson kernel from 0 to 2 pi. And one thing that we need to note is that the modulus of a must stay in between 0 and 1, or else none of this will work. That's one of the conditions of the Poisson kernel. And it's not important now, but it will be important later. So let's start. So we can get closer to a solvable form of this integral by saying that z equals e to the I theta power. This is a u substitution, or rather a z substitution. We could differentiate it, so now we have I times e to the I theta power d theta, and then we could substitute in the e to the I theta with the z because that was the original function, so now we have dz equals iz d theta. Therefore d theta is equal to dz over iz. So now we know that e to the I theta is equal to cosine theta plus I sine theta. If we use some complex algebra, we're able to determine that cosine of theta is equal to 1 over 2 times z plus 1 over z, and sine theta is equal to 1 over 2i times z minus 1 over z. For this video, we only need to know this and this. So we can delete everything else we know and save it on the side for us to use for a later reference. Okay, so we can substitute in all of our expressions accordingly. So now we have integral from 0 to 2 pi of 1 minus a squared times dz over iz times 1 minus 2a 1 half z plus 1 over z plus a squared. So now we'll just analyze the denominator, because the denominator is kind of annoying to deal with. So the denominator is iz times 1 minus 2a 1 half times z plus 1 over z plus a squared. One mouthful. So we can simplify this a little by saying iz is equal to, or iz times minus a z plus 1 over z plus a squared. And then distribute z to everything, so now we have just I times z minus a z squared plus 1 plus a squared z. And then we notice that the groupings of the terms are, with respect to a, we want to switch that to z. So now we have I times negative a z squared plus a squared plus 1 times z minus a. And then you can verify the algebra for that. And this is actually factorable. We can factor this in terms of z. And although it doesn't look easy to factor, this is actually equal to I times a, oh, there's a negative sign, negative ia times, or actually, it's easier if you write it this way, negative I times az plus 1 times z minus 1 times z minus a. So this is the factored form of this expression. Yeah, it's crazy how this can turn into this. So let's cross out all these crazy mathematics, and now we could just say that this is 1 over I of integral 0 to pi 1 minus a squared dz. Probably put a negative number here, then that's over az minus 1 times z minus a. And then we know that the kernel, a is just has to stay within 0 and 1. So z should also be staying within magnitude of 1. So we'll change this integral over to magnitude of 1, magnitude of z equals 1. And now we have a completely new expression. Okay, so now we have a semi-solvable form of the original integral, and now we can kind of transpose this into the Cauchy's formula. And if you remember anything from the Cauchy's formula, there's multiple of them, but one of them is 1 over 2 pi I of integral of magnitude z equals 1 of whatever expression you have here with z minus z0, z minus z1, that's equal to 1 over z0 minus z1, assuming that z0 is the 0 on the bottom that is found in the circle of magnitude 1. So given this, we can start working our way towards this form. So here we have 1 over I integral z equals 1 magnitude 1 minus a squared dz. That's equal to negative a z minus 1a times z minus a. So we can bring the 1 minus a squared out. So we have 1 minus a squared over I on the outside over z equals 1. That's equal to 1 over negative a z minus 1a z minus a. Okay, sorry if that handwriting is small. I'm bad at writing stuff, I guess. So now what we can do is, in order to make the Cauchy's formula true, we just take out the equal sign. We now have this. We can divide this expression by 2 pi I. And after that, we can get a form of Cauchy's solution, because we need the 2 pi I there first. So now that we have the 2 pi I, we can start solving. So we have z0, we can set this one to z0 and this one to z1. And this is because if you draw out a circle centered at the origin such that the magnitude is 1, we know that 1 over a is greater than 1 because it's in between 0 and 1, and a is in between 0 and 1. So a must fall inside the circle and 1 over a falls outside of it. That is why we said this one to z0. So with that being said, we now know that this is 1 over a squared, 1 over negative a times a minus 1 over a, which is equal to 1 over 1 minus a squared. So this 2 pi doesn't get transferred over to the other side, but this 1 minus a squared does. So now we could multiply this 1 minus a squared over, because that wasn't part of the original Cauchy's formula. So if this was originally 1, that would require you to multiply 1 minus a squared to both sides. So now we know this expression equals 1. So The only difference between this expression and this expression up here is this 2 pi factor from below. So therefore, this expression up here is 2 pi times greater than the one down here. Therefore, this is equal to 1 times 2 pi, or 2 pi. So let me erase all of this crap down here. If you want to see all the work, you should probably pause the video earlier on. So therefore, Poisson's integral is equal to 2 pi. And with all that work that I erased earlier, we have proved that Poisson's kernel is 2 pi. Yeah, that's a lot of work for a small little derivation, but it has consequences. Anyhow, thank you for watching this video. Hopefully you haven't gone by now because of how inactive I have been with uploading videos, and thanks for watching.